Right, this is a worked example for a moments problem. Um, and this particular problem relates to tipping. So this is a sort of typical kind of problem that you will get at A level. Let's have a look at the problem and we'll see what I mean. Okay, so we've got a uniform horizontal beam of length 6 meters and weight 600 newtons, supported by two ropes each attached 1 meter from the center. So here's the beam along here. Here's the center, and there is the weight shown as this arrow here, 600 newtons. A man of 800 newtons initially stood at the center of the beam. M walks rightward along the beam. Okay, so there he starts off, and he's progressed down to this point P. Um, what distance X meters from the center of the beam can he get before the beam tips? Okay, so what we can probably see intuitively here is that as he walks down the beam here, eventually, as he gets nearer to this end, then his moment, if you like, that is going to be increasing. At the start here, he's stood at the start. This is his initial position here. We can imagine what happens is we've got the weight of the beam, 600 newtons. We've got his weight, it's 1400. He is right in between these two ropes, uh, and um, and therefore there's a downward force of 1400. Then therefore must be an upward force of 1400 provided by the tension in these two ropes, and they are equally divided. That's 1400. So there's going to be 700 in each rope. Each rope is going to be pulling up with a force of 700. Now, as he moves to the right, what's going to happen is that this rope is going to take more and more of that 1400, and the rope on the left is going to take less correspondingly. So the total tension in the two ropes will still be 1400, and that is going to be the case because, of course, the upward analysis of forces remains the same. Um, Okay, so as this one increases, as T B increases, this one decreases, and eventually this is going to get to zero. Okay, and that is the point at which the beam will tip. Right, so how do we calculate that? Let's have a look then. So really what we're doing is we're just taking the moments about B. So the point being, therefore, that at the point it tips, the tension in this rope is zero. Right, so if we take moments about here, this is the most convenient place to take it because this then takes this particular force out of play. I mean, we know what it is, so we could take our moments about anywhere actually, and anywhere probably on the beam. Um, but it's just a bit more convenient to take it from there. It's an extra one term less in our calculation. So we take about there, and what have we got? Well, the clockwise moment is basically the weight of the man times his distance from P. That's 800, and that distance is well, it's this x minus this distance here. um, okay, so it's just that bit. Then, well, a sort of null entry really, because this, which right up to the point of tipping would have had a contribution, is now zero. So the fact that it's 2 meters from B is obviously therefore not really relevant. And then we've got the anti-clockwise moment, which is this 600, and that is 1 meter from B. Okay. So so we haven't tipped yet. So the total clockwise equals the total anti-clockwise. You can see this is just an equation in X. Okay, so that works out to be X is 14 over 8 or 1.75 meters from M. So this distance here is 1.75 meters from M. That is basically how it works. Should note that it also applies if these weren't ropes, but say they were sort of, supports there, then what we find is that the reaction force at this support here would actually become zero. So it's the same, but we're just using reaction forces instead of tensions. So hopefully that has been useful, and thanks for watching.